These are figures from a paper that Neil Abramson submitted in 1978 showing light in flight. So the system consisted of laser illumination where a pulsed spherical wave is incident on a mirror, which is here. And so as the pulse hits the mirror, some of the pulse proceeds and a chunk of the pulse is reflected up. So here in A, you see the pulse just beginning to hit the mirror. And then you see in B, C, and D the pulse moving away from the original spherical illumination. This was recorded in a single snapshot hologram, but then reconstructed by looking at the hologram from different directions with different illumination directions. So reconstructed by analog filtering of an actual physical hologram. Today, of course, we would use a digital recording system and computationally reconstruct the signal, and we'll discuss how to do that in this episode. Computational imaging. Episode 32, Temporal Holography. Over the last several episodes, we've considered how to propagate a coherent wave field when it's known on a boundary. We've discussed how to measure the wave field using holography or phase retrieval. And then we've discussed how to reconstruct objects given the wave field on a boundary. In most cases, we've focused strictly on quasi-monochromatic wave fields, so wave fields that oscillate at a single frequency, although at the end of our diffraction tomography discussion, we considered varying the frequency to get better resolution in reflection tomography. Today, we begin to discuss what happens if the wave field has a temporal dimension. In particular, we're interested in capturing pulses. We can use holographic interference to characterize temporal signals, just as we've used them to characterize spatial signals. Here we show a reference beam incident from this direction and a signal incident from this direction across a linear detector array. The signal that we would measure would be the time average irradiance of the incident beams, but the reference beam is propagating in one direction, and so you see a spatially and temporally distributed version of the reference beam illuminating the detector array, and then we're assuming that the signal beam is counter-propagating so that the signal that we measure would be the interference between these two. And in this case, we've assumed that there is no real spatial pattern to the signals. They consist only of temporal plane waves like the signal we saw Abramson reconstructing at the beginning of this episode. Now, when we multiply out this square, of course, we would have the magnitude of the reference squared plus the magnitude of the signal squared. But then we have cross terms that will have this form, where what we'll see mapped out on the detector array will be the convolution of the reference signal and a time-delayed version of the signal itself. And so the reference we can imagine as the impulse response in this system, and by analyzing against the reference, we can reconstruct the temporal signal wave. Here's an example of experimental data of this system, a signal consisting of two pulses and a single reference pulse. And you see that where the signal pulses are hitting the detector at the same time as the reference signal, we see interference fringes between those. And then if we filter on the interference frequency between the reference and the signal, we can reconstruct the envelope of the signal. Now, for this approach to work, we need to know what the reference is. And it turns out that there's no linear way for us to characterize the temporal shape of the reference wave. Various techniques have been developed to characterize the temporal shape of the reference signal. The most famous is called frequency-resolved optical gating, or FROG. And here we see a schematic of a FROG system drawn from the Swamp Optics webpage, one of the main purveyors of FROG systems. The basic idea is that you take in the unknown signal E of t and interfere with a time-delayed version of itself through a nonlinear material. As the pulse signal hits the nonlinear material, it generates a polarization, electromagnetic polarization at the carrier frequency in the material. But that polarization can have higher order terms that might be proportional to the field squared. So if the two pulses hit at exactly the same time, the field squared will be larger, and if they hit at some delayed time, then the amplitude of the field is smaller and the signal is smaller. So we can we can assure that the signal is hitting at the same time and map out its temporal shape, which is achieved using a phase retrieval. So the frog signal turns out to be the Fourier transform with respect to the time delay of the shifted version of the signal with itself in frequency space. This gives us a two-dimensional pattern in frequency space and time delay, or a spectrogram. So frog signals generate spectrograms as a function of the time delay. And from these spectrograms, then we implement iterative phase retrieval, essentially identical to the Gershberg-Saxton technique that we discussed in spatial phase retrieval in an earlier episode. After implementing this iterative algorithm, you can recover from the spectrogram traces here shown at the top the intensity and phase signals for the electric field as a function of time shown at the bottom. And again, this data is from Professor Kohler at Ohio State, but it's drawn from the Swamp Optics website. So through these kind of nonlinear techniques, we characterize the reference, and we know that we have a short pulse, and then we want to use the reference wave as a holographic reference to allow us to reconstruct a time domain signal. So unfortunately, we don't have a detector that can work at the picosecond to femtosecond times needed to characterize an optical signal. What we measure instead is the irradiance integrated over time, instant on a detector array, or alternatively, we can measure the power spectral density. So this would be the spectrum, the irradiance as a function of color on the detector. And so we separate the signal into its spectral components and measure those. And if we measure the magnitude squared of the spectrum of the unknown signal with the spectrum of the reference, then we would get the self terms and as a function of spectra and these cross terms. And so as an alternative to reconstructing the signal from the ballistic interference of the temporal signals, we can put the signal into a spectrometer and then try to isolate these interference terms. And if we know the spectrum, of course, the coherent spectrum of the unknown signal, then we can reconstruct the signal itself. So ideally, the reference signal, this R, would be a delta function, so that its Fourier transform would be a very broad signal, but with some kind of frequency modulation. So that frequency modulation would modulate this f of x of nu, and from that modulation we could filter and recover fx of nu. In the GitHub repository that goes with these episodes, there's a notebook which considers a simple example of temporal holography. So we're going to assume we have a pulse which consists of a sequence of signals, and that pulse interferes with the reference. So here's the this is for actually a 4-pulse sequence with this reference that's offset by 5 picoseconds from the signal, and so the interference frequency is 200 gigahertz when we offset by 5 picoseconds, and that corresponds to a wavelength oscillation in this interference of around 2 angstroms or 0.2 nanometers. So here we see that the spectrograph over 10 nanometers is going to have somewhere in the range of 50 oscillations or so, corresponding to the 2 nanometer frequency that is the beat frequency between the shifted reference and the signal. Now here the reference and the signal are collinear. These are plane wave pulses or just simple one-dimensional signals that only vary as a function of time. They're coming into the spectrometer, and they're coming in at different times, but they're interfered because the effect of what a spectrometer will do is take the spectral channels and separate them to measure them. Each spectral channel then is a much longer temporal signal, and so those interfere on the spectrometer even though the signal and the reference arrive at the spectrometer at different times in order to get this beat frequency. So in this particular case, the signal that generated this interference was this 4-pulse sequence shown here. So it's about 1 picosecond in duration, and it generates this interference term. And now if we take the Fourier transform of the interference term, we see a autocorrelation of the reference and the signal here near 0 time, and at the 5 picosecond time delay between the reference and the signal, we see the reconstructed recording signal. Now the signal has been blurred because the reference signal in this case is a 100 femtosecond long pulse, and so that acts as the impulse response for our measurement of the reference, and so the reconstructed signal is blurred by this interference with the reference. Now, so we've seen two different methods for characterizing temporal signals by holography. One method was to just take the light in flight and interfere with the reference signal directly. When we do that, the mean intensity that we see on all of the pixels is equal to the mean intensity of the signal. So there's a certain bias in the measurement. Alternatively, if we measure with a spectrometer, you'll notice that the beat between the different spectral components goes to 0 at some frequencies, and so there's not this bias background. That means that the spectral holography approach can measure the same signal but with much better signal to noise, because there's not a constant bias that will create shot noise on the background. So we can measure either method. Of course, it's the time domain interference, or to measure the time domain correlation function, or we can measure with the spectral approach, but the spectral approach has much lower SNR. So everything we've talked about so far, of course, is how would we characterize a one-dimensional time signal. But of course, the field is multidimensional. That we can have a space-time image, so that the field could have a different temporal signal at each point in 2 dimensions. And so ultimately, we'd like to think about how would we make measurement systems that could characterize pulses that look like this. This is a pulsed image, so each letter shown here had a duration of somewhere around 100 femtoseconds, and then so the light flying in space was going from letter to letter, and at the bottom here, for each cross or plus sign, you'll see a integral through time of what the temporal signal is for that pixel. So, for example, in the dark signal, you have the G is bright at 0, and so you see it bright, but then for the I, a couple of times, at 2 picoseconds, it's dark. So that trace is 0 here, but high here. And alternatively, this signal is 0 here, 0 here, but high here. So we need this kind of temporal trace for every pixel in the entire image. So in order to do that, we need to think about how we could use holographic methods to recover a space-time image. Now, the one downside again of the temporal interference approach is that we had to use a space, interference along along a path in order to recover the signal by interfering the temporal signal directly with the temporal reference. If instead we go to a spectrometer, what we need is a spectral image, right? If we could measure with the reference beam a spectrum for each pixel in the image, then we could use this spectral holography technique to reconstruct the space-time image. So that approach has recently been adopted by Jinyang Liang's group in Montreal, along with several other groups, where they use exactly the coated aperture spectral imaging system that we talked about in a previous chapter, as a spectral imaging system where you can add a reference beam to the signal with some time delay, look at the beat frequency, and reconstruct a signal. So in this case, we have a pulse coming into a CASSI system with time delay, and we see interference fringes in the spectrum measured by the CASSI system, and then by analyzing that interference signal, what can reconstruct the space-time signal in a single snapshot. So you have this single shot compressed optical tomography. So this is a general overview of how spectral interference can be used to create holograms that we can use to reconstruct time domain signals using spectral imagers and phase retrieval, the exact techniques that we've talked about so far in this course. So next time, we're going to continue our analysis of imaging with wave fields. And one of the key advantages of a wave field system is that we can measure the wave field on remote apertures, or measure the wave field remote to the detection aperture, and use that to project a synthetic aperture in space and create higher resolution images, or see through turbulence, or see around scatter. This is an example of using synthetic wavelength holography to image a scatter field and reconstruct an object while taking out the effect of the scatter. We'll discuss how that works in our next episode.